Welcome to Maths with EJD. In this video, we are looking at evolutionary algorithms for solving nonlinear programming problems. And so far, we have considered simulated annealing, which is patterned after cooling in metallurgy. Then we've seen taboo search, which involves some kind of memory. So you create a list of possible solutions with memory, so you don't revisit those parts. In this video, we'll be talking about genetic algorithm, which we have considered before for derivative-free methods under uh, optimization, uh, under numerical optimization methods. And after now, we'll be looking at particle swarm optimization. And after that, we will consider differential evolution. Okay. So, like I've said already, we've taken care of simulated annealing. We've talked about taboo search. Now we go for genetic algorithm. So, focusing on solving NLPs this time around, genetic algorithm for solving nonlinear programming or for nonlinear programming in short. So, let's see that. Genetic algorithms, or GAs for short, are optimization techniques inspired by the process of natural selection. And that is why it is evolutionary, inspired by natural selection. Okay. They are particularly, they are particularly useful in solving nonlinear programming problems where traditional methods, where traditional methods may struggle due to complexity of the objective function or constraints. Okay. Genetic algorithms genetic algorithms. Okay, I mean, we already know the short form, right? G is work by iterating over a population of potential solutions, evolving them through processes through processes like selection, crossover, and mutation to improve their performance in optimizing the objective function. So just like we've said, just like we've seen before, I'm just going to pick on the points one after the other. So let's look at steps in genetic algorithm for nonlinear programming. Okay, so the first thing is initialization, like we always have, initialization. So I won't write so much about this. I'll just talk. So for initialization, right, it generates an initial population of potential solutions, often randomly, just like what we did in the previous case, in the other video where I talked about genetic algorithm. Then after that, for each solution is represented as a chromosome, which is a vector of variables in the problem. Then after initialization, we go for selection. So, and what's happening here is you evaluate each solution based on the fitness function. That is the value of the objective function. So, since you are minimizing, we want to see what is as low as it can get. Then after that, we choose individuals with higher fitness to reproduce, typically using techniques like roulette wheel selection or tournament selection. Okay, so this selection here can be in two forms. We can have roulette wheel selection. We can also have tournament selection. Okay. Then the third step is about crossover, or what you can see as recombination. Recombination. So it's more like you're recombining the best of values for a stronger offspring. So, and for crossover, right, you combine parts of two chromosomes to produce two chromosomes to produce offspring mimicking biological reproduction. For example, two parent solutions might exchange segments of their chromosome to create two new solutions. And in step 5, we talk about mutation. Mutation. So here it's you randomly alter a part of a chromosome to maintain diversity in the population and help avoid local optima. So that's like mutation is a way of escaping local optima because we know that in non-linear programming, right, we have we have non-linear either objective function or non-linear constraints. And as a result of that, we can have the problem is more like it's not non-convex, and there's a risk of getting trapped in a local minimum. So it's mutation helps to escape that kind of thing. And in step 5, we talk about replacement. So in replacement, you replace the old population with a newly created offspring, sometimes preserving the best individual. That is elitism. So that's more like, a generation goes and another generation comes, and we expect the new generation to be better than the previous one, even in human populations. Then step 6 is about termination. Of course, there's always a need for termination, uh, based on certain criteria. So the algorithm terminates after a predefined number of generations or once the solutions converge to an acceptable level of optimization. So once you get the kind of population you want or the kind of solution you want, then you start thinking of termination. So let's move on to some worked example. Okay, so example, let's talk about non-linear optimization. So, and here, okay, we actually want to maximize. Is it maximize or minimize that it should really be? Okay, yeah. So let's just go for this. Maximize f of x because the standard is to minimize normally. So x1 squared plus x2 squared minus 5x1 minus 6x2. Want to minimize that subject to g1 of x equals x1 plus x2 minus 10 less than or equal to 0. And then we have g2 of x equals x1 minus 2 greater than or equal to 0. And then we have g3 of x equal to x2 minus 3 greater than or equal to 0. Okay, so we aim to maximize f of x satisfying the constraints. Okay. And to do that, we go for the first step, step one, which is to initialize population. Initialize population. Okay. So here we randomly generate an initial population of solutions. For example, let's say we generate 5 solutions. Um, Imagine 5 random solutions. Since you're talking about genetics, you can say chromosomes, right? Chromosomes. And they are down here. You have X1 to be 64, 28, 37, 37, 53, and 72. Okay, so you see we've generated those. Now you see that if we add the two together, they add up to 10, right? So we say each solution, each solution is a pair of values, is a pair of values, is a pair of values, x1, x2, which represent the variables of the problem. Okay, so with that in place, we go for step two, and that is where we evaluate fitness. So that's fitness evaluation. Fitness evaluation. So we evaluate the fitness of each solution by calculating the objective function f of x for each. So first of all, we have for x equals 6, 4. Okay, so we have f of 6, 4 equals 6 squared plus 4 squared minus 6 times 4. And that's what the expression is about. Okay, minus 5, 6, minus 6, 4. Okay, minus 5, 6, 5 into 6, minus 6 into 4. Okay, so that is 36 plus 16 minus 30 minus 24. So this is 42 minus 30, that's 12. 12 minus, so this is 36 plus 16, that's 52 rather. 52 minus 30 is 22. 22 minus 24 is minus 2. So we have that. We have f of 6, 4 to be minus 2. We have that. So the next one is 2, 8. So we have f of 2, 8 now. Yeah, let me not bother about writing that again. F of 2, 8 is simply 2 squared plus 8 squared minus 5, 2 minus 6, 8. Okay, so that is 4 plus 64 minus 10 minus 48, 48 rather. So this is 68 minus 48. That is 28 minus 10. 68 minus 48, right? Or rather, that, yeah, 68 minus 48, that is 20. 20 minus 10 is 10. Okay, simply 10. So f of 2, 8 is 10. So the first one was minus 2. Now this is 10. Okay, so we go for the next one, which is f of 2, f of 3, 7. So for f of 3, 7, we have 3 squared plus 7 squared minus 5, 3 minus 6, 7. Okay, this is 9 plus 49 minus 15 minus 42. Okay, 49 minus 42. Okay, 9 plus 49 is 58. 58 minus 15 is 43. 43 minus 42 is just 1. Okay, that is 1 like that. Then, we can continue like that. Okay, let me just try to complete all everything. That is 3, 7. So the next one is 5, 3. The next one is 5, 3. Oh, not everybody, everything has to 10. So we have 5, 3, and 7, 2. So let's do 5, 3, and 7, 2. So f of 5, 3. So we have 5 squared plus 3 squared minus 5, 5. Okay. Minus 6, 3. So that is 25 plus 9 minus 25 minus 18. Okay. So 25 and 25 will go. So 9 minus 18 is simply minus 9. So we have f of 5, 3 is minus 9. So finally, we have f of 3, 7. F of 7, 2, not 3, 7. F of 7, 2. So we have f of 7, 2. So that is 7 squared plus 2 squared minus 5, 7 minus 6, 2. So that is 49 plus 4 minus 35 minus 12, yeah? So 49 plus 4 is 53. 53 minus 35. 53 minus 35. Okay, this is 8. That's 18. So 18 minus 12 is 6. So 50, or rather 53 minus 12. 53 minus 12 is 41. So 41 minus 35 is 6. Okay, that works. So that we have f of 7, 2 to be 6. So we have all that result. Now let's look at the selection now. That's the next step, step 3. That's how we go for the selection. Step 3, selection. So based on fitness, select the parents for reproduction. Let's say for this example, the selection method is roulette wheel selection, and after evaluating all solutions, the top two solutions are 2, 8, and 3, 7. What are the top two solutions here? 2, 8, and 3, 7. Is that 2, 8 is 10, 3, 7 is 1. Okay, I think the top two are 3, 8, and 7, 2 here because they give us the best of the results since you are maximizing. Okay, so uh okay, so the top two solutions are x1 equals 2, 8, right? 2, 8 give us 10. Yeah, this is minus 2. Since you're maximizing, this is 10, this is 1, this is minus 9, and the next one is 7, 2. So 2, 8, 7, 2. Okay, so we have x1, x2 is 7, 2. So those are the two best results we have. 2, 8, 7, 2. So that is the selection stage. So these are the top two. So it means that these best two parents can give us the kind of children we want, the kind of offspring. And that takes us to step 4, where we cross them over. Step 4. So in step 4 now, we do the crossover or recombination. So perform crossover on the selected parent. For instance, take the first half of x1 and the second half of x2, producing two offsprings. So what we are saying is that, you have, from what we have, x1 is 2, 8, x2 is 7, 2. So since they give us the best results over there, so we can have two new offspring. We can have, so it's more like when you have 2, 8, and you have 7, 2, just like we have in biology. This is x1 and this is x2. So you can have 2 and 7. You can have 2 and 2. Okay, that's some standard biology thing. So you can have 2 and 2. So you have 2, 7. You can have 2, 2. Then you can have 8. You can have 8, 7. And you can also have 8, 2. So you can see it's really the biology, the genetic thing. So these are offspring. So perform crossover on the selected parent. For instance, take the first half of X1 and the second half of X2 and produce two new offspring. In fact, in this case, we have produced, now we have four new offsprings, in fact, four new offsprings from these two parents. Okay, so we have offspring one. The order doesn't matter because at the end of the day, it is the result they give us that will matter, right? So we can have 2, 7, okay, then we can have offspring 2, offspring 2, which is 8, 7. Then we have offspring 3, which is 2, 2, offspring 3, that is 2, 2, and finally offspring 4. So offspring 4, that is now 8, 2. So we have four new offspring from those two excellent parents from the previous generation. Okay, so we can go for step 5 now, where we talk about mutation. Step 5, mutation. So this is one way to make sure that our results, so because some of these offspring can even perform worse than the generation before them, so we want to get the very best. So for mutation now, we apply mutation with a small probability to maintain diversity in the population. For instance, mutate offspring one by randomly changing the second gene, giving, so we can say, for mutation now, we can just say, so look at all the offspring. We can just pick, okay, let's see. In the previous generation, right? We had we had 5, 3 not behaving well. We had 3, 7 not that good. We had 6, 4 not that good. So can we just look here and say, um so it looks like where the first value is very big. Okay, I don't know if that, I don't think that, I don't know. So we could just take something randomly. We could just say, we could just mutate offspring 3. So for offspring 3, we mutate so that 2, 2. So we can say 2, 2 now becomes something like 6, 6. Okay, that's some mutation for some kind of diversity in the system. So I mean that is done randomly. Okay, so that's why it can be a very tedious process, but thankfully we have Python to the rescue. So we go for step 6 now. Step 6, which talks about replacement. We have replacement in this place also. So you replace the least fit solutions from the current population with a new offspring. This ensures that the best solutions are preserved and gradually improved. So it means that now we can evaluate this, we can evaluate offspring 1. Okay, so we evaluate offspring 1, offspring 2. I think offspring 3 has been mutated, so we evaluate offspring 3 that has been mutated to 6, 6. We evaluate that, and then we evaluate 8, 2. So I mean the evaluation is substitute into that expression and you get the best results, right? So and once you have that, you do the replacement. So replace the least fit solutions from the current population with the new offspring. This ensures that the best solutions are preserved and gradually improved upon. So in short, the replacement is evaluate, evaluate the offsprings and preserve best solutions. Okay. So, I mean, I don't want to do that again. I just want to go ahead to coding, but you already know how to evaluate, so I won't even bother. So we now go for step 7. So in step 7 now, we have the termination. So repeat the process for a predefined number of generations. So after you get the best result from the 6 now, so you can pick the best two parents and do the whole crossing again and see how that goes. So repeat the process for a predefined number of generations or until the algorithm converges to an optimal or near optimal solution. After several generations, we find that the population stabilizes around a set of good solutions with, say, x1 is 3 and x2 is 7 as the optimal solution. So, in short, termination, repeat process until desired outcome, until desired outcome is achieved, until desired outcome is achieved. So that desired outcome could be a number of generations. Maybe you just want to do it for 5 generations. Whatever you get is what you get. Or you want to do it until you begin to get a particular kind of thing. Okay. All right. So Um, let's go ahead and look at the Python code in this situation. So this is it right here, 137 lines, I believe. Yeah. Oh, it's a lot. Okay, I think I'd even run it before. So let me clear that so we can see. Okay, so now we have here we are using random. Randomness is involved there because we just mutate the results, So here the problem we have is a maximization problem, right? So because of that we have a negative sign because it's this thing is standard for minimization. Because it's not maximization, we put negation sign, and then we have the variables x1 and x2. Then we define the constraints x1 plus x2, minus 10 is less than or equal to 0. X1 here is x of 0. That's the Python standard. Then the second constraint, we also have x1 minus 2 greater than 0. We have the third constraint, x1 minus 3 is greater than or equal to 0, like that. You can pick this code up from Facebook and study it and play with it and see how things go. So here we are taking a population of 50 and we are going for 100 generations, and we have two variables, right? So if you have three variables, you make sure the dimension is 3. So we have the bounds for x1 and x2. So we want the values not to go above 0 or 10, and below 0 or above 10. That's the bound for each generation. Okay, so if you run this, see what we get. Because there's a measure of randomness, each time you run it, you may get a different kind of result. Okay. But of course, if you want your result to be preserved, you can always, I mean, for whatever you do, right? You just see the solution now. You have 2.6 and 3.0, and the objective value is like minus 15.225. So because of the randomness involved, right? If I run it again, it also goes for different kind of selection, and then we still end up getting something close to the same kind of result. And the graphical solution is, so you see those red lines are possible searches, all the searches we did initially, but the blue star, the blue cross is finally where we got, where we finally get the result, right? So if I run it one more time, we discover that the solutions are, still pretty much around the same thing. So the best solution, the X1 is like 2.3 or thereabouts, the X2 is 3.0 thereabouts, and the objective value is minus 15.23 or so, So even with all the randomness involved, so we just have the solution hovering around all of those values. So I'll pick this particular one. So where x1 now is 2 decimal places, or let me say 4. So 2.4653, and x2 is 3.1333, whereas f of x1, x2, the max is minus 15.2310. So with this, we're done with Python, and we have our results. Imagine it's like 100 iterations, so it's a lot. So if you want to do it manually, generally speaking, doing all these evolutionary algorithms manually can be is I mean it's really tedious, but maybe in an exam situation we just be required to do one or two iterations, and then you have it like that. So from the Python code now, from the Python code, from the Python code, we see that x1 is equal to 2.4653, or I mean, instead of even doing this way, uh, from the Python code, right? We have x1 comma x2 to be equal to 2.4653 comma 3.1333, and the maximum value of f of x1, x2, given those values now, is simply minus 15.2310. All right, so that's how the genetic algorithm thing is. And in conclusion, we can say in this example, the genetic algorithm provides a heuristic approach to solving a nonlinear programming problem, finding a near optimal solution despite the nonlinearity and constraints. It can handle problems where classical methods like gradient descent or linear programming fail due to nonlinearity, non-differentiability, or complex constraints. Okay. So let's look at some practice questions. Or maybe I'll just take one. Anyone I can read out, I'll just read them out. And then we'll take one and we go from here. Okay. Looking for a nice one. Okay, good. I think I like this. So practice practice. So, maximize, want to maximize f of x equals 10, 10, right? Sine x1 plus 10 cos x2. That could also be xy, if you like. So subject to g1 of x equals x1 squared plus x2 squared minus 25 is less than or equal to 0. That's inequality constraint. Then we also have another inequality constraint, g2 of x equals x1. x1 now is greater than or equal to 0. And then we have g3 of x equals x2, which is also greater than or equal to 0. So we have a nonlinear objective function. We have the first inequality constraint is also nonlinear, and then we have linear constraints, so to speak. So what are the tasks here? So solve this nonlinear optimization problem using a genetic algorithm. Okay. Focus on one, choosing an effective population size. In the other case, we chose 10 population size, or 50 rather, from the code especially. Choosing an effective population size. Okay. And the chromosome representation. The chromosome representation. Then also focus on how to balance exploration and exploitation in the algorithm. Okay. To balance, in the algorithm, to avoid getting stuck. That's where mutation comes. Getting stuck in local optima. Then another part is the focus on the crossover, and mutation strategies you'd use to improve the solutions. Finally, what are the challenges you expect to encounter in this problem? Okay. So that's all we have for this. So feel free to put your solution in the comment, whether on Facebook or on YouTube. Also, let me know in the comment if you like me to solve a problem or teach on a particular topic. Feel free to let me know. And of course, let me also know. Okay, yeah. So if you have not subscribed, sorry, if you have not subscribed, feel free to subscribe. And if you have, thank you very much. And everybody, if you have subscribed, be sure to hit the notification bell so you can always get alerted each time a new video is released. And please be sure to share and like so that more people can have access to this great content. Till I come your way again, keep doing maths right. In the next video, we'll be talking about particle swarm optimization. Bye.